afternoon. Now, just to, so these are 5 short talks, 5 minutes each, no questions. I'm going to call them in the order that they appear in the program, and I will ask each presenter to share their screen, and of course subsequent presenters be ready to share your screen as soon as the previous one is over. And the first talk should be given by Tim Hele on a radical approach to highly efficient OLEDs. Tim, are you ready to share the screen? Can you do that?
Yes.
Thank you. Go ahead, please.
Can you see the presentation?
We can see it fine. You can go ahead.
Excellent. So, as Jay Nelson has said, I'm talking about designer lighting, a radical approach to improve organic light-emitting diodes. And I'm Dr. Tim Hele, and I'm a proleptic lecturer and Royal Society URF at UCL. So I realize many of you may be from physics backgrounds, and just a brief introduction to radicals. So these are molecules with 1 or more unpaired electrons, and that means that you have a highest occupied molecular orbital, which is full, a singly occupied molecular orbital, which is half full with just 1 electron, and then an empty lowest unoccupied molecular orbital. And historically, many known radicals, such as the chlorine radical, are unstable and dangerous, such as being used in the degradation of the ozone layer. And the few known stable organic radicals, such as the triphenyl methyl radical, are rarely emissive. However, in theory, there's no spin statistics problem with including them in OLEDs. And I realize for some of you, this will be familiar. So in a conventional organic light-emitting diode, where you have a HOMO or your valence band and a LUMO or conduction band, you would put a hole in the HOMO and an electron in the LUMO, and 3/4 of the time you'd end up with a triplet state, which is not emissive in an organic molecule, and 1/4 of the time you would have an emissive singlet. And if you do the same thing with a radical molecule, then regardless of the spin of the electron you take out of the HOMO, when you look at the electronic configurations you end up with, in either case you can emit. So in theory, you could get 100% internal quantum efficiency. And when you factor for the fact that about only 1/5 of the light that you generate, to 1/3, comes out of the device, I guess an external quantum efficiency of about 25%, which is greater than from conventional OLED materials. However, satisfying the spin statistics is a necessary but not sufficient criterion for emission, and you also need to have intense emission to not have non-radiative decay. And as I said earlier, because most known radicals are rarely emissive, for a very long time it was considered that radicals were a sort of obscure intellectual curiosity and not likely to work in OLEDs. So this is where me and my research come in. And in 2018, I was part of a team in the Cavendish who made this molecule TTM3NCZ, which you can see on the screen. And this is based on triphenyl methyl structure with a carbonyl group and various other things on it. And the OLED made from this had 27.6% external quantum efficiency. And this was a world record for any type of OLED or LED in the deep red and infrared. And also has a rather strange orbital structure, which is a bit difficult to see on a DFT calculation, but you have an orbital then a node, an orbital then a node, and so on. And I was able to explain using molecular orbital theory and group theory why this orbital structure existed. And so with that, it's possible to construct an MO diagram. Now, this is obviously a lot more complicated than the toy ones I showed you earlier, and then there isn't enough time in 5 minutes to derive it. But the key points shown on the right-hand panel is that if you have a doubly occupied SOMO from electron injection and taking an electron out of the HOMO, and an electron drops down, then it's this transition which has a non-zero transition dipole moment and leads to the efficient emission. And so we published this in Nature back in 2018. So this was quite an interesting piece of work. But immediately there are 2 questions. So firstly, why do some radicals emit when most of the known radicals don't? And is it possible to get emission in the visible as opposed to in the near infrared? And after a very large amount of theory, going back to certain bits of electronic structure from the 1950s, it's actually possible to prove algebraically that in order for a radical molecule that's conjugated with organic structure to emit, it must not be an alternate hydrocarbon. So what do I mean by that? It means that the molecule must have rings containing an odd number of atoms and or heteroatoms, such as nitrogen. And what you can then do is go to lists in the literature of people who've tried to make emissive radicals and see what works. And you can see that in all the radical molecules which work, which are on the right-hand side, they either contain nitrogen in the conjugated structure or 5-membered rings or both. And the structures which don't emit are entirely hydrocarbon and don't contain any heteroatoms. And so this is a really powerful design rule because it means you can often tell before you've synthesized a molecule or run an electronic structure theory calculation whether it's likely to work. And I would ask that if you know of a molecule which is an exception to this, then do let me know either by email or in the chat. So this was quite an interesting development, and we then were able to obtain radicals in the visible with fairly good external quantum efficiency, and that we published in Nature Materials. With that, I think I'm out of time. So thank you for listening.
Your mic is on, Julie.
Sorry. Sorry. I was muted. Tim, thanks very much for the presentation. Next up is Matthew Hodgson. And if you could please share your screen, Matthew. Matthew will talk about many-body excitation energies within Kohn-Sham DFT. So, Matthew, you've got 5 minutes. Please go ahead. Matt, we can't hear you. So Matthew, I'm not able to hear you, and I think if others can't hear you either.
No, I cannot.
Okay, Matt, there's something wrong. I can see that you're not muted, but we can't hear you. So maybe I don't know if there's something that the host can do with this.
I suggest moving on to the next speaker.
Let's move on to the next one, and we try to sort. Hosts will try and help you in the meantime. Matt, is that okay? Please stop sharing the screen for the moment. We'll come back to you at the end of the list, if that's all right. So the next speaker is going to be Julia Westermayr, who will talk about deep learning for efficient prediction of molecular electronic excited state properties. So Julia, you've already shared your screen, and please put it into presentation, and you've got 5 minutes.
Okay, so thank you very much for the introduction, and thanks to the organizers for giving me the opportunity to talk. I will dive into this topic by introducing you to the star of the presentation, which is fluorine. And fluorine is one of the molecules that plays an important role in optoelectronics due to its tunable optoelectronic properties. But it's not the only molecule that is important in this research field. There's also phenanthine, for instance, and it only differs to fluorine by 1 carbon atom, and yet it exhibits different optoelectronic properties. And there are also other molecules, such as members of the azine family, and dependent on whom you ask, you end up with about 10 to the power of 20 to 10 to the power of 60 molecules that could be of potential relevance to this research field. So if you want to decide which molecule is best for your purpose, it can get quite difficult. And these molecules can be characterized with photoelectron spectroscopy, and the charge transport properties are usually characterized by the level alignment of the donor and the acceptor molecules. So for instance, we can use photoemission spectroscopy to probe the occupied states. And we can do this either by going to the lab, synthesizing the molecule, and then measuring it. But unfortunately, as you might know, experiments are expensive, and it is also limited because we don't know whether the molecule that we are interested in is yet synthesizable. And this is exactly where theory comes in. And we can use it to compute photoemission spectra, and on one side to complement experiment and to compute them of molecules that are not yet synthesized. Unfortunately, theory is also kind of limited because to get accurate spectra, it is also quite expensive. And our solution to this problem is, as a solution of many other people, machine learning. So what we did was we developed a machine learning model that was trained on orbital energies of the OE62 training set. And this is a training set that was developed to advance the research field of optoelectronics. So it's a spectroscopy data set of functional organic molecules, and it contains 62,000 data points of orbital energies at a DFT level of theory. So we trained a machine learning model on these orbital energies, and then we predicted the photoemission spectrum at almost no computational costs. And you can see here the photoemission spectrum and the peak of the LUMO orbital. And when we compare to the experimental spectrum of fluorine, it didn't match our predicted spectrum. And this was expected because DFT is not the best method for this purpose. So what we needed was higher accuracy. And fortunately, this training set also contains a subset of 5,000 data points at a GW level of accuracy. So we used the first neural network as a step one and augmented the orbital energies with a second machine learning model that was trained on the difference between DFT and GW. And in this way, we obtained quasi-particle energies. And if you're more interested in the technical details, you can look them up in our current archive paper. So we then used the second machine learning model, and we again predicted the photoemission spectrum of fluorine. And you can see here that the spectrum matches the experimental spectrum much better than DFT. And we also wanted to know whether the model can be used for different molecules that are similar in the structure but have different optoelectronic properties. So we computed the spectrum of phenanthrene, and you can see here again the spectrum at the DFT level of theory, which doesn't match the experimental spectrum. But if you look at the GW spectrum that was augmented with the second machine learning model, you can see that it matches experiment quite well, and the machine learning model can distinguish between different molecules. And both of these molecules are not included in the training set. So I could come to a conclusion. We developed a machine learning model to predict orbital energies and quasi-particle energies of many diverse molecules. And I hope that I could show you the relevance of this model to photoemission spectroscopy. And as an outlook, we aim for high throughput screening. And with this, I want to thank the funding agencies, Reinhard Maurer. And if you're more interested into this topic, you can look it up at these references. And thank you for your attention.
Brilliant. Thank you very much, Julia. That was fantastic. And you kept very nicely to time. So I'm going to go on with the next speaker on the list, which is Anna. So Anna, if you can share your screen, please. So Anna Youngbluth.
My screen right now.
So thank you.
Sorry.
So Anna is going to talk about charge transfer processes and voltage losses of dilute solar cells based on fluorinated zinc phthalocyanine. Anna, please go ahead. You've got 5 minutes.
Thank you. Let me just start sharing again. Can you see my screen?
Yes, I can.
Awesome, thank you. Yeah, so my name is Anna. I'm a PhD student at the University of Oxford, and today I will talk about dilute solar cells based on fluorinated ZnPc. In this work, we study fluorinated ZnPc molecules as donors paired with C60, and we fabricate dilute bulk heterojunctions with 5% donor content in C60. These dilute heterojunctions are quite interesting because all donor molecules are fully surrounded by C60 and donor aggregation is suppressed. And this makes dilute solar cells an excellent model system to decouple energetic and microstructure effects. In the fluorinated ZnPc molecules have attracted quite a lot of interest in literature, and it has been shown that fluorination shifts the HOMO and LUMO simultaneously away from the vacuum level. This keeps the singlet energy approximately constant, but allows us to tune the energy of the CT state at the donor-acceptor interface. And this has been demonstrated, for example, for one-to-one blends in the work of Bendoun et al. The 4 ZnPc C60 system has already been shown to be a low offset system, so we were quite interested to see what would happen if we fluorinated the molecules even further. And specifically in the case of F16 ZnPc, we were interested if we might create a type 1 heterojunction or even fully reverse the donor acceptor system. So the first step was to look at current voltage curves. And for this, we found that with increasing fluorination, the open circuit voltage increased and the short circuit current decreased. From what we know about the transitions between ZnPc and F4 ZnPc, this was kind of expected, and with a reduced energetic offset at the interface, we would find reduced voltage losses, but also less efficient exciton separation at the interface. But the same logic extends past F4 ZnPc. What was surprising, though, was that the dilute F16 ZnPc system behaved pretty much the same as a pure C60 device. And this suggests that F16 ZnPc does not really participate in the free charge generation. We also had a look at the EQE, and on a log scale, we were able to get a first indication that the CT state energy increases across all systems. To have a look at some of the relevant energy levels, so as expected, our optical gap of the system stayed roughly constant, and we performed standard Marcus theory fitting to determine CT state energies. And the measured open circuit voltage tracked quite well the changes in the CT state energy. We could then look at voltage losses across the whole spectrum and found that the voltage losses reduced for all of these different systems. A large contribution of this will be a reduced driving force between the S1 and the CT state. However, we weren't really sure if we intuitively expected these changes also for F16 ZnPc. So we performed frontier orbital calculations that confirmed that we might create a type 1 heterojunction. But what we were curious about was why F16 ZnPc was not acting as a recombination center. So that sort of suggested that we needed to look at our materials a little bit more holistically than just to look at the HOMO and LUMOS. And so what we did next was to have a closer look again at the energetic offset at the interface and comparing it to the reorganization energy of these systems. So these reorganization energies were determined experimentally. And it's been mentioned a few times before, but the reorganization energy describes the amount of energy that a molecule can minimize if it undergoes a charge transfer. And what we found is that in the case of F16 ZnPc, the reorganization energy was larger than the energetic offset. And so that allowed us to draw up a schematic of what the potential energy landscape might look like. And so here I'm showing the S1 on the left and the CT states on the right for ZnPc and F16 ZnPc for simplicity. And what we found is that we might have an energetic barrier at the donor-acceptor interface in the F16 ZnPc case, which might make charge transfer via the CT state less likely. And we have since done a few other measurements that confirm this hypothesis, specifically electron paramagnetic resonance measurements and temperature-dependent EQE. And all of this will be included in the manuscript that we're writing up at the moment. And the very last comment that I want to make is that, of course, this system lends itself perfectly to be studied by more advanced charge transfer models that take tunneling into account or hybridization between different energy states. And that's actually something that we're currently exploring with the help of Jean-Luc Breda's group at the University of Arizona and hoping to apply their 3-state model to these systems. And so, yeah, thank you very much for your attention, and thank you to all of my colleagues for supporting this work.
Thank you very much, Anna. Again, kept well to the time. I'm going to go straight on with the last talk on the list. We'll then come back to Matt. And the next one is Alessandro Landi, is going to talk about a quantitative prediction of the electromechanical response in organic crystals. So Alessandro's already shared his screen. Please go ahead, and you've got 5 minutes.
Okay, thank you for the presentation. Hello, and I will talk about the prediction of electromechanical response in organic semiconductors. As you know, these materials have several favorable properties, such as better processability, finely tunable electronic and chemical properties, and above all, considerable flexibility. This latter characteristic is at the basis of several cutting-edge applications, depending on whether the material's conductivity shows a marked variation with strain, which is useful in pressure sensors or schemes, or conversely, if there is a certain stability of the electrical properties, which is mandatory for flexible solar cells or bi-integrated circuits. In the last years, several organic semiconductors have been investigated. However, significantly different electromechanical responses have been found. In particular, experimental relative changes in the carrier mobility per unit of applied strain ranging from 0 to 250% have been reported for rubbing. These widely different experimental findings could have several causes, such as the presence of residual defects in the crystal or a partial stress relief in the elastomeric substrate over which the crystal is laminated. In this respect, the development of a reliable computational protocol would allow to separate the intrinsic material response from extrinsic effects in the interpretation of experimental results and could also be used to identify new promising materials. Several theoretical works have been performed on this topic, relying either on molecular dynamics or on full DFT optimization of the crystal cell under strain. Then, charge mobility are calculated using Marcus theory or through the transient localization theory. This latter model has been developed by one of the speakers at this workshop, so you know everything about it, but it builds up on the widely accepted evidence that in organic materials, the transfer integrals between two neighboring molecules undergo large fluctuations, giving rise to a dynamic disorder which causes a localization of the instantaneous eigenstates of the lattice. This model has demonstrated a high level of predictive power, leading to results in agreement with experimental data and other more computationally intensive approaches. However, the fluctuations can be computationally expensive to evaluate, in particular when periodic full DFT calculations are used. So, in order to develop a method that can be used as a predictive tool for the analysis of new materials, we have tried to lower the computational burden by resorting to the density functional tight binding method, which has demonstrated to lead to geometries and energies in good agreement with DFT methods at much lower cost, as Marcus told earlier. So, what is our method? We rescale axis and molecular position according to the strain applied. Then we use the FTB to optimize the unit cell and evaluate the crystal phonons in a 2 × 2 × 1 supercell. Then the transfer integrals and the fluctuations are evaluated using the formula here reported. Our investigation on rubbing showed that uniaxial strain applied either along the A-axis or along the B-axis result in an increase in mobility, the latter being higher in magnitude in good agreement with experimental findings. This difference is easily rationalized by observing that compression either along A or along B axis results in a similar increase of transfer integrals, but the latter leads to a decrease of the dynamic disorder. Moreover, compression along A-axis leads to a decrease in the intermolecular distances between the molecules along the pi-staking direction, which have a trivial effect on the calculated mobility. Our investigation also indicates that some other systems have mobility along the pi-staking direction very little dependent on strain, which is a very appealing feature for their exploitation in flexible electronics, where indeed a preservation of electrical performances under mechanical deformation is required. As you may have noticed, so far we have focused on a limited range of applied deformation, since the vast majority of organic semiconductors have never been analyzed under strain larger than 3%. A remarkable exception is TIPS, for which charge mobility has been measured under both compressive and tensile strain up to 16.7%, showing outstanding increase in the charge carrier mobility under compression, a behavior well reproduced by our methodology. In conclusion, our results point out that electromechanical properties vary by orders of magnitude within the class of organic semiconductors, and this is due to the different intrinsic response of the materials, not to device artifacts or other extrinsic effects, as long disputed in the literature. This finding highlights that there is plenty of room for the identification of new compounds, either very sensitive or insensitive to deformation, for application in cutting-edge technologies such as wearable electronics, tactile sensors, or skins. And with this, I would like to thank the organizing committee for having given me the opportunity of presenting my work, and of course, you all for your kind attention.
Thank you very much, Alessandro. Good timekeeping again. So we're going to come back to the last talk. So Matt, if you could share your screen again, and hopefully we will be able to hear you this time. And I would just say, I should have said it earlier, we can't have questions after the lightning talks, but if anybody has a question for one of the 5 speakers, please feel free to write it in the chat, and the speaker will, I'm sure, be very happy to try and answer it. Okay, Matt, so let's try again with the...
Hear me now?
Yeah, we can hear you. Great, fantastic.
Thank you. Yeah, so I'm going to discuss how we can obtain many-body excitation energies from a system of non-interacting electrons. So on the left, we have the many-body system of interacting electrons, and on the right, we have the corresponding Kohn-Sham system. And the Kohn-Sham system is defined to give the exact many-body electron probability density, regardless of how many electrons are in the system. So as we increase the number of electrons, we see that the number of interactions in the many-body system increases, whereas within the Kohn-Sham system, the electrons remain non-interacting. However, as the electron density has to reproduce the effect of the Coulomb interaction for this system of non-interacting electrons, the external potential, or the Kohn-Sham potential, adapts in order to ensure that no matter how many particles we have in the system, the electron densities of both systems matches. The advantage of this is, of course, the computational scaling for the Kohn-Sham system is far more feasible than a system of interacting electrons. However, just because the electron density of the 2 systems are the same, it doesn't necessarily follow that the other observables match. So how can we calculate excitation energies from the Kohn-Sham system? Well, first, we have to determine if there is an exact relationship between the excitation energy we want and the corresponding quantity in the Kohn-Sham system. And if there is, we can develop an approximation which captures this relationship. So as an example, we might consider charge transfer in the Kohn-Sham system. My colleagues and I demonstrated that regardless of the complexity of the system, if we consider the transfer of charge within the ground state Kohn-Sham system, upon charge transfer, the exact potential discontinuously shifts by this constant delta CT. Delta CT can be used with the charge transfer energy in the Kohn-Sham system to obtain the exact many-body charge transfer energy. What's important here is that we don't need to actually model the transfer of charge in order to obtain delta CT. Therefore, in principle, from the ground state Kohn-Sham system, we can obtain the many-body charge transfer energy. There are other examples of this, such as the addition of an electron to the system causing the jump in the potential delta, which can be obtained in this case with a charged excitation to obtain the fundamental gap, or for a solid, the band gap. So the question is, how can we exploit this property of the exact Kohn-Sham potential in order to obtain excitation energies from approximations to the Kohn-Sham potential? So consider the local density approximation, which is a very computationally cheap approximation. And we defined this fictitious classical charge density, which yields the Hartree exchange correlation potential of the Kohn-Sham system. And we can show analytically that this charge density has a total charge Q that is equal to n-1 for a system of n electrons. So we enforce that this total charge density itself is discontinuous upon, for example, the addition of an electron. And we find that in the corresponding local density approximations potential, we obtain this discontinuous shift needed in this case to obtain the fundamental gap. So in conclusion, excitation energies can be obtained for the Kohn-Sham system, but we have to obtain them via these discontinuous shifts in the Kohn-Sham potential. We constrain the commonly used local density approximation to obtain an approximation to the discontinuous shift in order to calculate the fundamental gap. And in the future, we hope to formulate more constraints that are capable of yielding other excitation energies, for example, charge transfer or the optical gap. Thank you.
Thank you, Matt. Thanks again for keeping to time brilliantly. We now have so thanks to all of you giving your talks very rapidly. And as I said in the last moment, anybody in the audience who wants to ask a question to any of these talks, you can use the chat, and I'm sure the speakers will reply.